Welcome to Auto 155, Electricity and Electronics 1. My name is Tony DeBlasi, and in this lecture I will be covering the cranking system. This is part 1 of a 2-part lecture based on Chapter 52 from the Automotive Technology, Principles, Diagnosis, and Service 6th edition. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the course content folder. Please note that there are both audio and visual lecture attendance codes scattered throughout this lecture. Please write these codes down as you see and hear them. At the completion of this lecture, you will be required to go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture. The following is an overview of the objectives covered in this lecture. I will describe the parts and operation of a cranking circuit and explain computer-controlled starting. I will discuss how a starter motor converts electrical power into mechanical power. I will list the different types of starter motors. I will describe gear reduction starters, and I will describe the function of starter drives and solenoids. The information found in this chapter will help you prepare for the ASC Electrical Electronic Systems A6 Certification Test Content Area C. Essentially, with a cranking circuit, the parts that are involved, there's several components, but we'll kind of go in order. You have your starter motor, obviously, and your starter motor is normally running between about 0.5 to 2.5 horsepower, it can actually produce up to 8 horsepower during the initial engagement. So we'll talk about how a starter spins really fast at first and then kind of slows down. You can even see that on a waveform when you measure starter's voltage. They can produce around 0.4 to 2 kilowatts. So that's quite a significant amount of electrical energy. I know that the starter initially will spin the motor at around 200 RPM, getting it to indeed start. So the other part is the battery, obviously. That's a big part. We covered that last week. Now, with regard to the battery, it has to be at a minimum of 75% state of charge or 12.4 volts. If you have a battery that's any less than that, then the starter cannot spin at that 200 RPM or that 2.5 horsepower in order to turn the motor. The next thing on our list would be our starter solenoid. Now, when I say solenoid and relay, I have both of them up here. Many systems contain both, and we've covered what a relay and a solenoid are. Relays can carry 30 amps, up to 30 amps, and solenoids can carry, hundreds of amps. The relay may be in series, or the relay may control the actual solenoid itself. There is the starter drive, which contains the pinion gear that will engage with the flywheel ring gear. And then we have, finally, the ignition switch. That's the part you're engaging with, so your fingertips are touching. So that's the key in the ignition, or it could be your push button, or it could be remotely. However it is, that's the part that you engage with. So an important item to note with regard to how we control the starter is that the ignition switch itself does not operate the starter unless certain safety functions have been followed. So in an automatic transmission, it needs to be in either neutral or park. And if it's a manual transmission, obviously the clutch pedal would need to be depressed. Older vehicles, you could just turn the key and start them. If it was a manual transmission, you could just turn the key and it would fire up. And if it was in gear, the car would lurch either forward or backward, depending on what gear it's in. Vehicles of today with manual transmissions are equipped with a clutch safety switch. So the clutch pedal has to be depressed, which could also be a diagnostic point, a failure point, or when you're going to start a vehicle that has a manual transmission. In my experience, I've received some vehicles that supposedly needed to be, they thought the starter was bad. Well, when I stepped on the clutch, it fired up. They just weren't stepping on the clutch enough. The other thing, too, is I will try to start a vehicle in both park and neutral to verify if it's not the neutral park safety switch. Chapter 52, Lecture Code Question Number 1. Please write this down. 34210. Once again, that is 34210. Please write that down. So right here we have a picture of a starter. And you can see the solenoid mounted on top. I'll actually bring my mouse in here so you can see. So there's your solenoid, and there's your starter motor. Now, what you can see pretty well is you can see the BAT terminal, or BAT, or B nut, that has steady power from the battery, right? Notice that's a pretty large cable because there's a lot of amperage that has to go over this wire. What we can't see, and it's out of frame, is there's usually a signal wire, which is a small wire. So B for big, S for small. Really, technically, it's B for bat and S for signal. Those wires are important. So there's 3 terminals on a starter solenoid. There's one for the B, there's one for the S, and then there's a third one down here. You can usually see it's an uninsulated braided cable, and that wire is the M nut, right? So as current passes through the switch exists between the B terminal and the M terminal and carries current down into the actual starter motor. Here we are looking at the ignition switch, and there's 2 parts really. There's the mechanical lock cylinder, and then you have your electric ignition switch. So right here, here's the lock cylinder that's basically designated to be paired with a particular type of key, and then as it slides in, inside of our ignition switch is the actual electrical switch that will send the signal either directly to the S terminal or to the powertrain control module, PCM, which will then initiate starting of the vehicle. Here is an overview of how that system essentially functions. So here's our ignition switch right here. If you close this switch, current will then flow down to a second safety switch, and that switch, if it's a automatic transmission, it will have the neutral safety switch, and if it's a manual transmission, it will have the clutch switch. So if these 2 switches are closed, it will allow current to flow down into my starter at the S terminal, and the S terminal, that is the power side, kind of similar to our 86 on a relay. That will allow current to flow in and energize this coil. And when this coil is energized, it will then pull a plunger back, completing a circuit here. And if you notice, I have a battery cable that runs directly down through this circuit to my B nut or my B post. And that's where essentially our pin 30, if we were to compare it to a relay, that's waiting to go into this pin right here, which would be similar to 87, which would be the output to our load. And in this case, our load is the starter motor. And ground in this case for the load and for my solenoid is through the actual chassis of the starter itself. So you can see here the ground symbol. Now, with regard to computer-controlled starting, which is essentially most vehicles now, as far as operation goes, the ignition switch start position on the push-to-start button is used as an input signal to the powertrain control module, the PCM. So essentially, it becomes a sensor, and the vehicle will not be allowed to start if A, your foot isn't on the brake, B, your vehicle's shift select is not either in park or neutral. There's a lot of criteria now that's going into vehicles, so they can't be started unless there's someone in it. With regard to remote starting, when we talk about remote starting, we're talking about factory installed remote starts. They allow the driver to start the engine from a distance of around 200 feet through buildings. And during this time, the doors will remain locked to reduce the possibility of theft. There are also aftermarket remote starting systems, and those are quite common, but we're not going to discuss a lot of those today, but just understand they are out there. Now, with regard to operation of a computer-controlled starting system, the theory of operation is normally the cranking speed from your starter would be, like as I was saying, around that 200 RPM. So it'll vary between 100 and 250 RPM. Now, what the computer is doing, the computer is looking for 400 RPM or to exceed 400 RPM. If the computer sees through the use of cam and crankshaft position sensors, if it notices that the engine is turning at a speed greater than 400 RPM, then the PCM will see that the vehicle has started. And at that point, it will open or turn off the S terminal or the S circuit voltage. It'll take it away, and what that'll do is it'll actually shut the starter motor off. So that's how it knows the vehicle started. Now, there's also a timeout period where the PCM will deactivate power to the starter if the engine doesn't start or for some other reason. This is to prevent the starter from overheating. Now, this can throw people off, or it started to back in the day, when you would go to start your vehicle and let's say it didn't have gas in the tank, or you had a bigger problem like an ignition system issue or a fuel system issue. You would turn the key, the vehicle would attempt to start, and then you'd let go of the key, but the vehicle would continue to keep cranking. We called that ghost cranking. And it's very common now. You're probably familiar with it. It'll run for a predetermined amount of time and then shut off. Computer-controlled starting is almost always part of a push-button system. Here's an example of a push-button start-stop. This is off a Jag. So obviously, to make these work, you'd have to have your foot on the brake and the vehicle in park when you go to push that button. And also the key would need to be in the vehicle. And here's an example of the key, or the fob, I should say. And if you notice at the top of the fob, right here, you have a button with a kind of a circular arrow. That's a remote start. Chapter 52, lecture code question number 4. Please write this down. 501152. Once again, that is 501152. Please write this down. Now, as I stated earlier, starter motors are going to use, obviously, our electromagnetic principles that we've discussed prior in the semester to convert our electrical energy that we're putting to it from the chemical electrical energy from the battery to produce up to 300 amps, on a larger engine vehicle or on a cold day. So we're looking between typically 1 to 300 amps on a starter to get a vehicle going. That mechanical power is producing, as I stated earlier in this lecture, it's producing up to a possible 8 horsepower to turn our motor over, or 6 kilowatts. So or to turn our engine over. That's a pretty significant amount of energy. So once again, it can't be understated that the starter is the largest electrical load in a modern vehicle. Now, there are a couple of different kinds of motors out there. So we're discussing motors right now, not necessarily starters, but motors in general. And starters are typically series style motors. A series motor develops its maximum torque at the initial start. So when we first go to start it over at 0 RPM, it's going to create a significant amount of torque and obviously use the most amperage. It will develop less torque as speed increases. So this is pretty much by design. So a series motor develops less torque at high RPM because a current is produced in the starter itself that acts against the current from the battery. Because this current works against the battery voltage, it's called counter electromotive force, so CEMF. Just to kind of summarize this, the starter will make its own electricity. Yes, we are taking electricity to make a mechanical energy, but the starter also makes a quick burst of its own power called counter electromotive force, CEMF. If you recall, earlier in the semester, we were talking about Lenz's law and induced voltage or induced current, where we would take a magnet and push it through a coil. Well, as we discussed with Lenz's law, the current that is produced from the magnet being pushed into it, that is inducing it, will create its own magnetic field around the wire that will counteract or fight against the magnet that is creating the induction to begin with. So I know that's a mouthful and hard to follow. Just understand that as a starter takes power, it makes power at the same time, and those two forces or those two magnetic fields will actually push against each other and fight each other. So that's why we use a series motor. Typically in a starter, it'll start out nice and fast, but then as it starts to generate its own power, it will actually slow down. Now, if we're going to be discussing motors, we're going to also talk about shunt motors. And a shunt motor is a parallel motor, not a series motor. And that's basically the field coils will be in parallel. A shunt motor does not decrease in torque at higher motor RPM because the counter electromotive force produced in the armature does not decrease the field coil strength. So that being said, a shunt motor does not produce as high a starting torque as that produced by a series wound motor, and it's not used for starters as a rule. Some small electric motors, such as those used for windshield wipers, maybe a window regulator, those might be small enough, and those will be the shunt style motor. Pretty much all cars nowadays are using the permanent magnet gear reduction style motor. So the second bullet here, permanent magnet motors. Those are the ones that you'll see, as far as having permanent magnets lining the case. It's pretty much the common in most automotive applications nowadays. But they'll use a gear reduction to multiply the starter torque. They spin so fast, so they take that speed and essentially convert it into a mechanical energy using planetary gears. Compound motors have some of the field coils connected to the armature in series, and some of them are connected directly to the battery in parallel. So that way you get kind of the best of both worlds. You'll see this in some Ford, Chrysler, and GM type starters. Now in this diagram here, we have the old school field coils or pole shoes. So you can see here a series wound starter or a series wound motor, where the wire comes in, it wraps around the north pole shoe, comes around, and then wraps around the south pole shoe, and then terminates in series with the hot brush or the positive brush. And then you have your commutator segments here. This would be a perfect opportunity for me to share with you some of the clips from the Films on Demand site provided through the SMCC library.
Note the battery symbol in this starting circuit diagram. It connects to the starter solenoid. The ignition switch feeds current to the starter solenoid when the driver turns the ignition key to start. When the ignition key is turned all the way, a small current flows through the solenoid windings, ignition switch, powertrain control module or PCM, and back through the battery. This energizes the solenoid and closes its contacts. A very high current can then flow through the starter motor, the solenoid, and battery to crank the engine. A starter motor relies on strong magnetic fields for operation. A permanent magnet and a current-carrying wire both produce a magnetic flux or field. Since magnetic fields can attract and repel each other, they can be used to produce strong rotational forces inside an electric motor. A simple electric motor uses stationary field magnets that act against a rotating set of windings. A commutator and brushes feed current into the rotating windings. Current flows through the brushes, the motor windings, and back to the battery. The center frame is the foundation of an engine starter motor. It holds and supports the other major parts. The brush end frame connects to the rear of the center frame, and the drive end frame connects to the front or other end of the center frame. Field coils or permanent magnets mount inside the center frame to produce a stationary magnetic field. Armature bushings fit into the drive and brush end frames. They are used to support and allow the armature shaft to spin freely inside the starter motor assembly. The commutator mounts on one end of the armature shaft. The brushes rub on the commutator to produce a sliding electrical contact when the motor is running. Armature windings fit inside a metal armature core loaded on the armature shaft. This produces a very strong rotating magnetic field. A pinion gear is splined onto the shaft for engagement with the engine flywheel ring gear. A one-way clutch is constructed as part of the pinion gear to keep the flywheel ring gear from spinning and damaging the motor when the engine fires and runs on its own power. A lever arm is used to push the pinion gear outward whenever the starter motor is engaged. A plunger and sometimes a pull shoe are used to act upon the lever arm. Some starters use a solenoid to physically move the plunger, lever arm, and pinion gear back and forth. This close-up shows the commutator segments. Each segment is connected to an armature winding. Insulating material is undercut and separates the commutator segments. This allows the brushes to feed current into each set of armature windings individually. On the other end of the armature shaft, Note that a groove is machined for a snap ring. Spiral splines on the shaft are used to make the pinion gear and clutch turn with the shaft, but they allow the gear to slide back and forth. Some starters have a thick C-clip type snap ring like this one to secure the pinion gear assembly. A cup-type washer fits over the C-clip to protect it. This starter cutaway shows how the commutator end of the armature shaft mounts in bushings in the end frame. A thrust washer often fits between the armature and the brush end frame. The soft metal bushing press fits into the end frame. Grease reduces friction between the bushings and the armature shaft. Starter bushings are usually made of a soft brass-bronze alloy to reduce shaft wear. This animation shows field coils mounted in the center frame. They produce a strong magnetic field, which repels and attracts the magnetic fields produced around the armature. Note the large wires that feed current into the starter brushes. Approximately 100 amps can be fed into the starter when energized. This high current produces a strong magnetic field, which is powerful enough to spin the engine crankshaft. In the past, most starter motors used heavy-gauge field coils mounted around iron pole shoes. The magnet and windings produced a stationary field. Now, the trend is to use high-power permanent magnets only without the field windings. This reduces motor size, weight, cost, and complexity. Long bolts feed through the brush end frame, center frame, and thread into the drive end frame to hold the starter motor together. By removing these two bolts, you can disassemble the starter. Large holes in the thick drive end frame are provided for bolting the starter motor to the engine. An opening is provided so that the pinion gear can engage the flywheel ring gear. Here, you see a starter motor attached to the side of an engine. The starter normally bolts to the engine block or to the clutch housing. A strong mounting of the starter motor is needed to keep the pinion gear and ring gear meshing quietly.
This concludes the Part 1 lecture for Chapter 52, the cranking system. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the Course Content folder. Now that you have completed this lecture and you have written down the online lecture attendance codes, please go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture.